Hello, everybody. Boom. Alright, so first thing we're gonna do is I need to pull up Mischief. I have to explain something. This is for the archive. I don't know if anyone will catch it now. If anyone does catch it now, we might have an interesting conversation, but this is for the archive. I had a realization this morning, something that bothered me. And then I tried to explain this little epiphany I had, and people were having trouble following me, as is usual with Twitter discourse on subtle topics. So I want to explain myself fully, and then explain the various ways of resolving this problem that I've found since this morning, and especially the one that I think is most elegant, the easiest one. All right. Hobner Coinbase says he's broken. I don't know what that means. Hopefully it's not too bad. Okay, so here's what I was worrying about this morning. We're all gonna have to do a little bit of math here, and we're gonna have to do some proofs. So I'm gonna start by showing the proof that I've shown. Now it could be that, or that I've been shown. It could be that I was shown a particularly sloppy presentation of it, or one that was watered down, etc. But it always stuck with me that there was something. It just felt like a little bit unrigorous, this particular proof, and I always felt like they probably have a more rigorous proof than that, and they're just not explaining it. But that probably does it. And as far as I could tell, I couldn't think of the problem, so I just let it go. But this morning I woke up and I had thought of what the problem was. After years, I just woke up and I knew what the problem was with this proof. So let me explain to you the proof I've always seen. First of all, we're talking about real numbers, and I'm going to use the fancy pants notation of real set versus the natural numbers. Right? So this over here is the set of real numbers. That's this guy. This is the set of natural numbers. So these sets include things like the natural numbers are 1, 2, 3, those numbers, dot, 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 all the way up. The real numbers are things like 1, 2, and 3, also -1 and 0, and 2/3, and pi, right? All of these are real numbers, and anything basically that you write that has the form digit, 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 right? Oop, oop. Get back to the pen, if Mischief will allow it. Right, if it's digit, good look. Digit, 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 dot, digit, digit, If you write numbers this way, you're getting yourself a real number. Might be transcendental, might be algebraic, might be rational, might even be an integer, might even be a natural number. But those are our real numbers. Okay, so now we know we're on the same page of what numbers I'm talking about. It's generally held that the real numbers are uncountable. That is, the cardinality of this set is greater than the cardinality of that set. And cardinality is a special term that you use for sets, because once you have infinite sets, size doesn't exactly apply. Right, they don't have a size per se, but they still have this concept of cardinality, which basically has to do with, can I make a bijection between these two sets? If I can make some function of x such that I can use that function to map from the real numbers, technically I just need an injection to make it a countable set, right? If I have this injection here, where where every real number maps to a unique natural number, then we have, it is the case that these two are equal. But if it is not possible to make this f, then r is greater than n, right? And this is, I'm not arguing with this. This is correct, and we'll see why. But first I have to show you the proof I'm normally shown. So, here is the proof that I have normally been shown. Consider the subinterval, from 0 to 1, right? This is a subset, not subinterval, it's a subset of the real numbers, yes? Dumb looking R. There we go. It's a subset of the real numbers. So if this set here is uncountable, then the real numbers are certainly uncountable. So we can represent those numbers as follows, right? 0, point, and then a string of digits, right? And this is where it gets a little informal and always made me uncomfortable. Say like A1, A2, A3, but whoever has seen variables, ... out to infinity, whoever has seen variables being the digits in a formula, right? That's not actually like a thing that you do. It's like not how you write these things formally. So whenever I saw this, I was like, okay, we're taking a small leap away from rigor here, but not a big one because it's not too hard to imagine how you would turn this into a rigorous thing. It's just this infinite sum from n equals 1 to infinity of a n times 1 over 10 to the n, right? That's not terrible, and we have mathematical ways of talking about infinite sums. We've defined that concept. So it's like, okay, it's not too worrisome that we're doing this unrigorous thing. I kind of see how we could get it better. The idea is, say that we have this mapping, right? We're trying to build a mapping to these natural numbers. 1, 2, 3, right? ... And the diagonalization proof goes like this. Construct some diagonal, let's call it D, some number, some real number, that's supposed to be in this interval, 0 to 1, so 0 dot, right? And construct it in the following way. Take the first digit and put something other than A1 there, right? So I'll call that A1 star. Any digit other than A1 would suffice. And B2 star goes here. Right, so the idea is I'm going down the diagonal where whichever index I'm at, basically, whatever I'm mapping to, I take that digit and I put it into my new number, but then I change that digit. I make sure that the one digit I put there does not match the one digit in that row. And the idea here, ... is that no matter which row you pick, you can go out and out and out forever. You pick the 1,000th row, the 10,000th row, no matter which n you pick, this D will not be the number at that row. Therefore, this is not a complete list no matter what you say, right? That's the idea. And the reason D isn't in this picture is because, look, it doesn't agree with 1 because the digit there is different. It doesn't agree with 2 because the digit there is different. It doesn't agree with 3 because the digit there is different. That's the proof I normally see, and normally that was fine for me. I looked at it, I was like, you're right. If the two digits disagree, it's not the same thing. This morning I woke up and I gasped because here's a totally unrelated concept. You can see these videos all over the place on YouTube. It's the idea that 0.9 repeating equals 1. I don't feel like defending that, but the idea is that if you take, you can still make it rigorous, which is to say you can take the 9 over 10 to the n as you sum that from 1 to infinity, and the mathematical definition of an infinite sum says that this equals 1, right? Now, just to be clear, that's our mathematical definition, right? It might be an arbitrary definition, but the way you sum infinite numbers is defined. We've chosen a definition, and the definition we've chose says this. So this here is a problem for the thing I was talking about up there, because you can take this and you can find other examples of this. For instance, 0.09 repeating is equal to 0.1, right? It's the same thing, but we've shifted it by 1. That should be the same number. If these two things here can be the same number, then this proof up here has a problem. Because now we were implying that because this digit and this digit are different, that these numbers must be different. But I've just shown that this first digit and this first digit could be the same, and there's a 0 repeating here. Could be the same, could be totally different, yet the number be the same. And in fact, every digit of this number is different, and yet the whole number is the same. So this isn't actually a proof that's totally rigorous. This assumes that every decimal expansion is unique, because the conclusion it makes is, look, I found a decimal expansion not on that list, and then it makes the leap to, therefore D is not on that list. But you can't actually make that leap. But that's fine. There's all sorts of ways we can actually prove that n is less than r. That the cardinality of n is less than r. It's just that this morning I wasn't thinking clearly, and it just occurred to me they've been glossing over this forever, and now that I see that I have to double check. I have to double check that we know for sure, because if I'm not double checking that I know for sure, then I'm failing my mathematical duty as a math enthusiast to make sure I know everything for sure, right? And if every mathematician was like that, we would have a problem. So we can't let anyone be that way if we can help it. Now I've got all of these things in nice little boxes. In the last box we're going to do, put this in here, is we're going to say, last thing we're going to do is we're going to say, let's prove this properly. We're going to make this proof work now. So there's all sorts of fancy ways you can do it. All sorts of fancy ways you can do it, and the thing is, I don't feel like explaining them. Like, I went through a couple of them involving limits on intervals, which, you know, roughly helps, and there's all sorts of things that you can do that kind of show this, but they involve some pretty complex stuff. And I know a lot of people considered all kind of great things, and I was happy to read all of them because I'm always happy to learn that kind of stuff. That's not the. I'm not upset that I read all those. It was all good. And the more complex a proof is, sometimes it lets you learn things along the way, and that's always nice. But someone suggested a really nice way to make this proof work, and that is, we've chose the wrong subset. Now we're going to pick a new subset. We're going to pick a subset. Let's call it, I don't know, X. And that's going to be a subset of the interval from 0 to 1. And this subset, again, if I prove that X is uncountable, then this is uncountable and R is uncountable. And the rule for being an X is, there exists X, let's say X small is in X, the set, if and only if X is equal to this decimal expansion. I'm going to do this all rigorously so that there's no question whether or not it's a fair proof. Is equal to this decimal expansion, right? A n 1 over n to the n, and a of n is equal to 0, or a of n is equal to 1 for all n, right? So this is the kicker. This is the change right here. Because of that, we have a different subset. We're not just talking about this interval. We're talking about this interval with the property that there is some decimal expansion which is all ones and zeros. Now, it's not necessarily a unique decimal expansion. It's not necessarily the unique decimal expansion. we could do some work and figure out whether or not it always is unique, but it's always the only decimal expansion of only ones and zeros, right? There's never any, in this base, right? If we went to binary, then if you're in binary, 1.0 repeating is equal to 0.1 repeating, right? In binary. But in base 10, and any base other than 2, really, if it's all zeros and ones, then there's only and you can, if you can express it as zeros and ones, there's only one way to express it as zeros and ones. These are unique, right? There's one unique way to satisfy this condition for x if you can satisfy it at all. So that means the diagonalization proof will work, right? So now we have 1 is the sequence of a's, 2 is the sequence of b's. These are all ones and zeros. 3 is the sequence of c's. And we make a new sequence by flipping each bit. So we say D equals A1 star, B2 star, etc. Right? You get the idea. So, same idea. Now we just need to make double sure that what I said was true. Don't let anyone ever pass something by you in maths. Your job is always to prove the thing. Always take the time to know for sure, because, you know, it's the only chance you ever get is math to know something for sure. So always take the time to know for sure. So let's be absolutely sure that this is a unique decimal expansion with this requirement applied, okay? So, suppose we took, for instance, the decimal, or the sequence AK, right? Let's say case 1, A of 1 equals 1, right? Then let's introduce this function. So let's call E the expansion function that takes in a sequence and it outputs x, which is, you know, the sum of the sequence, right? We've written this, but I'll write it one more, all the way to it, right? So expansion of a sequence looks like that. Okay. So if A is 1, that's our first case. Then the expansion of this AK is equal to 1/10. You agree? Because n equals 1 means that we're doing 1 times 1/10 plus the expansion of everything after AK, right? Of sequence AK plus 1. So we don't have AK in there, right? This notation here is a little imprecise, but I hope you get what I mean. If we pull the A1 off, then everything else still sums up to the same thing, and we just add the 1/10 in ourself, right? Now, let's suppose, in this case, that we find a new sequence. We'll call it D, for the diagonal down here, D of DKs, right? Like Donkey Kongs. Such that the expansion of this sequence is equal to the expansion of the AK sequence, and D of K equals 0. For that to be true, it must be that there is some, that, you know, that everything in there, DK, the expansion of DK, has to equal 1/10 plus the expansion of everything else. AK plus. Alright, so here's where the problem is going to arise. If DK is 0, if we're assuming that it's possible to change this bit, right, then we can see that this expansion here has to add up to 1/10 plus all of that other stuff without that, right? But the problem is, if I take the sum, even if every other bit is on, the sum of 1 over 10, the n, starting from n squared, right? Because I'm excluding the case where n equals 1. We're saying that should be d1. Okay, assume d1 equals 0. So starting from n equals 2, the sum of this is only 9/100ths. That's the definition of that. That's how infinite sums defines this particular sum. 1/100th plus, is that even right? Is it 9/100ths or 9/1000ths? 0.111111 is, oh no, I'm wrong. It's not 9/100ths. It's 0.111111 is is 1/9, right? So that's actually 1/90th. That's what it should be. All right. Okay. Anyway, even if we sum up everything else, it's only 1/90th, right? Further, if we take the case where some arbitrary a I is 1 and di is 0, then the expansion, you see where this is going, of ak is equal to the expansion of everything in ak except for ai, right? Turning ai into, ignoring the ai expansion, plus 1 over 10 pi. This is not the imaginary unit, this is just a variable, right? But the problem is, this guy here, if we assume that everything before the AI was zeros, right? That makes our life easy, because then we'll just get something like this again, except it'll be that the sum from n equals I plus 1 onward, you know, that sum there of 1/10 can't possibly add up to enough to make the thing that we're missing, right? So the thing that we're missing is 1 over 10 to the I. So this is always going to be less than 1 over 10 to the I, right? Now I said assume that the first part is 0. So again, question that. If everything before was 0, it makes it easy. What if everything to the left was non-zero? Well, finally we can see that if, for example, I look at this as an inductive thing, right? I said A1. I said I can generally say that if AI and this are the same, are different, right? And everything before it was 0, then there's a problem. Now let's say everything before it was non-zero. Well, we know that if the first two don't match, if the first pair doesn't match, it's a problem. So we can say that the first two have to match, assuming that AI must match di for I less than n, right? For everything before this, so set n equal to 2 to begin with. Assume that all of those match, which we know they have to match for the case of I equals 1. So we have our base case, we have our inductive step. Then we can subtract, we can say that the expansion of AK minus everything before AK. So basically the expansion from A1 to AI, right? Or AN minus 1, right? So if we take that out, that's going to have to be equal to the expansion of the same thing for D again, dk, right? minus the expansion for d1 to di minus 1. Why do these have to be the same? Because we're trying to say that this and this are the same, and we know that this and this has to be the same by assumption, right? In fact, they have to be the same sequences, so those are the same. So that means these two will be the same if these two are the same. So now, as we've seen, if everything, after doing this, the number we get here is all zeros left of the nth digit, and this number is all zeros left of the nth digit. So as we showed here, the next digit has to be the same, right? So by my second point, I'll call these points 1, 2, and 3. 1, 2, and 3. So by my second point, a n has to equal dn. Therefore, we've seen that these decimal expansions are unique, and therefore the diagonalization proof holds, and therefore r is greater than n in cardinality, right? So obviously, I went into depth there, but the reason I went into depth, the reason I cared about doing that is because I get annoyed whenever I find out that someone's proved something to me and done it sloppily. I don't want to do the same thing. If there's anything in here that I skipped over, it was this, right? This stuff about how to take infinite sums. And the reason I skipped over is because it's just a definition, and I don't feel like teaching limits. I don't have time for that. But if you want to be a proper maths hobbyist, you should find that out for yourself. You should make sure that you agree with me there too. And you should also hopefully see why this version of the proof, without limiting ourselves to a subset that only uses ones and zeros, this version is actually a little bit flawed. Obviously, what I showed was also not the most elegant proof because I only showed it for a weird subset of 0 of the interval there. But, and it's the subset defined by the existence of these sequences. It's all well defined and it's correct. It's certainly not elegant. You could do it with limits and things, as I was saying. Don't feel like teaching it. But there's my bit on R and N. Real numbers are in fact uncountable, and I just had to make sure of it this morning. So anyways, thank you for following along with me for 30 minutes, it looks like, as I did this tedious in-depth proof. I was just in the mood. I'm going to stop the recording and start it again, or stop the stream and start it again, and then I'm going to get to working on the tree generator.